In this chapter, we'll be doing basic functions and symmetry. So we'll start with symmetry. So there's a couple different kinds of symmetry for graphs. The two that we'll be doing is y-axis symmetry and origin symmetry. So starting here with the y-axis symmetry. So we say that a graph has y-axis symmetry if it's a reflection of itself over the y-axis. And these functions that have this symmetry are called even functions. So for example, let's say we have a graph that looks something like this. And we'll call this f of x. So it looks like this has y-axis symmetry, meaning if we took one side of the y-axis and reflected it over to the other side, it would lie right on top of itself. So looking more in depth at this, that means if let's say we have this x value right here, and it corresponds to that y value up there, that means if we take the negative version of that x value over here, meaning -3 instead of +3, it's going to correspond to that same exact y value over here. So what that means in more of a mathematical sense is that a function is an even function with y-axis symmetry if f of -x equals f of x. So if we plug in a -x, it's going to give us the same y value as if we plugged in a positive x. So that's how we check if we're given the function and not the graph. To check if a function is even, we plug in -x into all of the x's, and then we simplify it, and if it simplifies to the original f of x, then that means it is an even function with y-axis symmetry. So let's do some examples here. Let's show that f of x, which is x to the 4th minus 2x squared plus 1, is an even function, meaning it has y-axis symmetry. So what we're going to do is we are going to evaluate f of -x. So we plug in a -x everywhere there's an x. So that becomes -x to the 4th minus 2 times -x squared plus 1. And this simplifies to a negative x raised up to an even exponent is going to be the same as positive x to that exponent. So we get x to the 4th minus 2, -x squared. The squared is even once again, so the negative ends up canceling and goes away. So we end up getting x to the 4th minus 2x squared plus 1. And we can see that this is actually equivalent to the original. So this equals f of x. So since f of -x equals f of x, this is an even function, meaning it has y-axis symmetry. Okay, next one for origin symmetry here. So a graph has origin symmetry if it's a 180-degree rotation of itself about the origin. So what that means, if you take a graph and you flip the paper completely upside down 180 degrees, it would look exactly the same as it did before you flipped it. These types of functions are called odd functions. So an example of this would look something like this graph here. And we'll call this one f of x also. So notice that if you took your head here and you completely looked upside down, it would look exactly the same as before you flipped your head upside down. So that means this has origin symmetry, meaning it's a 180-degree rotation of itself. So let's take a look at this x value right here, x equals 1. So the y value for this is right down here. It looks like -2. So if we look at -1 this time instead of +1, the y value is up here this time at +2. So that means if we negate the x values, we're also going to be negating the y values. So in a more mathematical sense, this means that a function, this should say odd function down here. Okay, so a function is an odd function if f of -x equals -f of x. That means if we plug in the negative x values, it's going to give us out negative y values from the original. So to check this, to check if a function is odd, we're going to plug in negative x's once again into all the x's. This time we're going to see if it simplifies to negative of the original negative f of x. So let's do an example of this one. So we want to show that f of x equals negative, or f of x equals 2x cubed minus 5x is an odd function. So once again, we start with f of negative x. And we plug in a negative x into all of the x's, and we get 2 times negative x cubed minus 5 times negative x. So a negative x raised up to an odd power is going to remain negative, and the parentheses get dropped. So this first term is going to become negative 2x cubed. And the second term is minus 5 times negative x. That's going to become plus 5x because the negative and the negative make a positive. And we recognize that this is not the same thing as the original, so we know it's not an even function. If we factor out a negative 1 here, what we end up with is negative, and then what's left over is 2x cubed minus 5x. So we factored out the negative 1. And now we recognize that what's inside those parentheses is the original. So this is negative the original. This is negative f of x, which means that this is an odd function. So odd function meaning it has origin symmetry. So this little note here at the bottom, if f of negative x does not equal the original, and if f of negative x does not equal negative f of x, then the function has neither y-axis nor origin symmetry. Okay, so that is the two main symmetries that we'll be dealing with. Now let's move on to the basic functions that we'll be working with. So basic functions, or they're also called parent functions, are just these certain functions that get used a lot in mathematics with graphing. So a couple that we're going to be doing here are the identity function, the squaring function, square root function, absolute value function, and the cubing function. So I'll go through and take a look at each one of these and their properties. So starting with the identity function. So the identity function is f of x equals x. So remember here that f of x is the same thing as y. It's y equals x. So let's come up with a little table of values here and plug in. So I'll plug in -2, -1, 0, 1, and 2. So plugging these into our function f of x would be f of -2 for this first one, which is just -2 because f of x equals x. So plugging it in is just going to be itself, which is why it's called the identity function. So plugging in f of -1 would give us -1. F of 0 is 0, f of 1 is 1, and f of 2 is 2. So pretty much one of the easiest functions that we can work with here. So these are all xy coordinates, right? The first one, -2, -2, would be right down here. Then we have -1, -1, 0, 0, 1, 1, and 2, 2. So connecting these, we get this line. So this is the identity function is our basic linear function. Okay, so some properties here. The domain is -infinity to infinity. So is the range, and this has origin symmetry. Okay, next one is the squaring function. So the squaring function, called the squaring function because it's f of x equals x squared. So let's plug in some values here so we can graph it. I'm going to use the same x values. I'm going to use -2, -1, 0, 1, and 2. So plugging these into the function, f of -2 would be -2 squared, which gives us a +4. So make sure when you're plugging in values, you're using parentheses. -2 squared is +4. If we do f of -1, that's -1 squared, which is +1. If we plug in f of 0, we get 0, f of 1, we get 1, f of 2, we get 4. So just skipping those and just filling it out real quick. So plotting these on our xy plane here on the right, we get the coordinate -2, 4. negative 1, comma 1, 0, comma 0, 1, comma 1, and 2, comma 4. So connecting these, we get this graph right here. So the x squared, we should have known that this was not going to be a linear function. This is a quadratic, a degree 2 polynomial, and the shape of this is a parabola. It's that U shape. And just as a reminder, this little point down here, this turning point is called the vertex. Okay, so that's parabolic. And a couple of the properties here, the domain is negative infinity to infinity. The range is 0 to infinity, including the 0, because we can include it. And the symmetry is y-axis symmetry. It's a mirror image over the y-axis. So this is an even function. Okay, and next one, square root function. The square root function is f of x equals the square root of x. So picking a couple points to plug in. So I'm going to plug in 0, 1, 4, and 9. So I'm plugging these ones in on purpose because, first of all, we can't plug in negative values into the square root function. And I'm picking values that are going to give us out nice rational numbers, nice whole numbers out. So starting with 0, f of 0, the square root of 0 is just 0. Plugging in a 1, the square root of 1 is 1. Plugging in a 4, the square root of 4 is 2. And plugging in, lastly, for 9, the square root of 9 is 3. So plotting these points on our graph on the right here, we have 0, comma 0, 1, comma 1, 4, comma 2, and 9, comma 3. And connecting them gives us something like this. So this is actually, this similar shape is a parabola that has fallen over, but it's missing this other portion down here. So it's essentially half of a parabola that is horizontal instead of vertical. Okay, and then some of the properties we have, domain and the range are both 0 to infinity, including the 0, and this does not have y-axis nor origin symmetry. Okay, do a couple more here. Next, the absolute value function. The absolute value function is f of x equals the absolute value of x. So I'm going to use negative 2, negative 1, 0, 1, and 2 to plug in for the x values. So plugging in f of negative 2, that's the absolute value of negative 2, which is just positive 2. Plugging in f of negative 1, that's the absolute value of negative 1, which is positive 1. Now plugging in a 0, we would get 0. Plugging in 1, we would get 1. And plugging in 2, we would get 2. So plotting these as xy coordinates, we have negative 2, comma 2, negative 1, comma 1, 0, comma 0, 1, comma 1, and 2, comma 2. And we would end up getting this V shape. So it's essentially composed of two linear functions here. So this point right here is not a vertex. So the vertex was for the parabola. This is a sharp turn. This is a sharp corner, rather. And the sharp corner is called a cusp. So a vertex is a smooth turn. The cusp is a sharp point. Okay, and then the properties for this one, domain is negative infinity to infinity, range is 0 to infinity, including the 0, and the symmetry, as we can see, it is an even function, meaning it has y-axis symmetry. Okay, and we'll do one more here, and this is the cubing function. The cubing function is f of x equals x cubed, and I'll use those same values that I've been using, negative 2, negative 1, 0, 1, and 2. So plugging in a negative 2, f of negative 2 is negative 2 cubed. So this is a negative to an odd power, so it stays negative. Negative 2 cubed is negative 8. So plugging in negative 1, negative 1 cubed, negative to an odd power once again, the negative stays, So this is -1. And then we get 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. Okay, so plotting these, we get -2 comma -8 down here, -1 comma -1, 0 comma 0, 1 comma 1, and 2 comma 8. And we connect them and get something like this. So we can see that this, that for the domain and range and the symmetry here, the domain and range are both -infinity to +infinity, and the symmetry is origin symmetry. Okay, so it looks like that is it for this section with symmetry and the basic functions that we'll be using going forward.